Hi, so today I'll talk about the interior regularity of area minimizing currents in high codimension. So what's the starting point? Well, of course, as you'd expect, we start with the plateau problem, which very loosely stated says, given a boundary, which is say -1 dimensional, what are the surfaces of least area that span this given boundary? Area that span. Right, so yeah, this is very vaguely stated what the plateau problem asks. And okay, there are a number of things to make sense of here. Firstly, what do we mean by boundary? What do we mean by surfaces? What do we mean by area? And what does it mean to span? So I apologize in advance to those of you who already know about currents. I'll just give a very brief review. So of course, very natural setting in which to pose this problem is the setting of m-dimensional currents. So for a start, you could ask, well, why is this not well posed in, say, the topology of smooth surfaces? And the problem is that you lack compactness. So this is, you'd kind of want to solve the plateau problem using the direct method. You take your infamizing sequence of say smooth oriented surfaces spanning your given, say, smooth boundary. You take these so that their areas converge to the infimum, and you want to understand what the limit is. But you might have there are many examples you can construct that lack compactness. So, you have this kind of very obvious example where you take the gamma to be the boundary of the disk. So in 2D, and you start taking these things where you kind of take a cap and you add tentacles to it. So take something like this, you add tentacles, and this is really kind of rounded. And then the next element in your sequence, you flatten this cap a little bit and you add longer and thinner tentacles, maybe more of them, and they can do really wild things. And you keep doing this, and you construct this sequence of surfaces sigma k such that the areas converge to the area of the disk, but there's no compactness in any CK topology. So this is bad. So we need to to make this problem well posed, we need to ask this question in a weaker setting. And that's exactly what, why we need currents. So what is an m-dimensional current? An m-dimensional current is, which we call T, is a bounded linear functional on the space of M forms. So it's an element of space, which you write as this. Yeah, so you feed it in an M form, and yeah, this it's a continuous linear function on these guys. So for example, in particular, if you take a smooth m-dimensional oriented, so note that in this definition, it's kind of implicit that currents come with an orientation, right? Because ebb forms orient surfaces. So if you take a smooth oriented m-dimensional manifold, then you can induce a current that acts via integration over this guy, which we write like this. So this naturally induces the following current that really just integrates your M form over your surface, as you would expect, right? this space of n-dimensional currents comes with a boundary operator. So we have boundary operator, which takes the space of m-dimensional currents to the space of m-1 dimensional currents. And it acts by duality. So as you'd expect, it acts by, you apply t to the exterior derivative of your m-1, of your m-1 form. So once again, this is very natural. It naturally extends Stokes' theorem. So again, if you consider sigma to be smooth oriented surface with a boundary, then the boundary acts again via integration over the boundary of your surface. So this is an m-1 form. But now by Stokes' theorem, this is equal to integrating the exterior derivative of your m-1 form over your m-dimensional surface. And this, as we already defined, is exactly how you identify an how you induce an naturally induce an m-dimensional current from sigma. So we define the boundary so that Stokes' theorem holds in a weak sense for m-dimensional currents. And we also have a dual notion of mass or area, which again is defined by duality, right? So this is the supremum, but m forms of comass at most 1. Yeah, so very natural. Okay, but now the entire space of m-dimensional currents is too big. There's too many wild things can still happen. I mean, these guys are just dual to the space of m forms, but unfortunately, they don't sort of naturally generalize really like smooth oriented surfaces as much as we'd like them to. So for example, if you take, if we take an m-dimensional current T with bounded mass, then by the Riesz representation theorem, we can associate a vector valued measure to this guy. So there exists a vector measure which takes values in this this wedge space. So we write this measure with a bit of an abusive notation as follows. So this is the vector density or the polar of your measure, which its image is in the, so I guess, is in the space of m forms. Oh, sorry, in in this wedge space. And this is this guy is the mass of the measure, such that, right, so we can identify this measure with T in the following way. But unfortunately, just because T is an m-dimensional current, it doesn't tell you that this measure is m-dimensional. And like it's not necessarily absolutely continuous with respect to m-dimensional Hausdorff measure sitting on any reasonable set. So for example, you could take, I mean, there are many silly examples you can construct. I mean, you could take your current that just sort of picks up information about your m forms from a single point or from any lower dimensional space than m-dimensional. And then the associated measure, so in the case of a point, would be like a Dirac, or, this is pretty bad. We don't want to consider currents like this. So hence we reduce ourselves to, so we consider the subspace of this space of m-dimensional currents. Of integral m-dimensional currents, which we usually write in this way. And this is defined as follows. So we say that T is an m-dimensional integral current if both T and its boundary are of the following form. So they take an M form, or an M-1 form in the case of the boundary, and you map it to a superposition of, so it acts on these forms by sort of essentially both T and its boundary are a superposition of sort of relatively nice m-dimensional surfaces with integer multiplicities. So L equals 1 to infinity, where so these multiplicities kappa L are integers, and these KLs are closed subsets of some C1 surfaces. These are m-dimensional surfaces. So yeah, as I said, both, m-1 dimensional in the case of the boundary, right? So yeah, as I said, essentially integral currents are those where both itself and its boundary is really a superposition of nice oriented surfaces with multiplicities. But this doesn't rule out the fact that you can have things like this. So this is an example of, I guess, a one-dimensional integral current, and you maybe weight this with multiplicity 2, this with multiplicity 3. So you create these places where you create these singularities, which I'll define properly very soon. But these places where locally around this point, you can't write your surface as really just a single nice smooth guy with some multiplicity. Okay. So and another very nice property of the space of integral currents is that now we have compactness in this class. So this is due to Federer and Fleming, which tells us that there exists, and this gives existence of a minimizer in every integral homology class. So there exists an area minimizer T in every integral homology class. So in particular, if you take a sequence of nice smooth oriented surfaces, you take an infimizing sequence. So you fix your boundary, take an infimizing sequence of smooth oriented surfaces, then okay, you don't have compactness necessarily in the smooth topology or any CK topology, but you do have compactness if you sort of induce the associated m-dimensional integral currents to these guys, and you take compactness in that class. So what I mean more precisely is, given integral current S, there exists an integral current T with T being in the same homology class as S, and such that the area of T is the infimum R tilde such that R tilde is in the same homology class. Right. Okay, cool. So yeah, this explains why the space of integral currents is really a natural one in which to pose the plateau problem. Of course, it's not the only natural setting. I mean, there's been a lot of work done where you replace integral currents with currents mod p. So you take your multiplicities modulo p for an arbitrary integer p. Yeah, there's been a lot of work on this, I guess, starting from maybe Gene Taylor, Brian White, more recently, Delelis, Hirsch, Marchese, Stuvard, and Spolaor, and probably a bunch of others that whose names I forgot to mention. My apologies if I've forgotten anyone. Okay, but we focus on integral currents here. Right, and then as I promised, let me define what it means for to have singularities, because now we allow for these things as sort of this picture I drew. So because we now pose things in this weak setting, we allow the formation of singularities. So what does it mean for an integral current? So from now on, T will always be an area minimizing integral current if I don't write this otherwise. So we say that, firstly, let me define what it means for a point to be a regular point. So you say that a point in the support, and by support of T, I mean the support of this measure that you get this via the Riesz representation theorem, which for integral currents now is really like the m-dimensional Hausdorff measure, which comes from the superposition of the m-dimensional Hausdorff measures on all of these surfaces that you get in this representation of T with the appropriate weights from the multiplicities. We say that point X in the support of T is a regular point. Should we write X in T if X is in the support of T outside? So also, as the title of this talk suggests, we'll only be dealing with interior singularities. So my regular and singular points will be interior points. So I look so locally around this point, you don't see any boundary of your surface. I mean, there's also a bunch of work that's been done and being done on boundary regularity. In my opinion, this is a much harder problem and much less has been understood in general. There's been, again, a lot of work on this by many, including Hart and Simon in codimension 1. They showed the absence of singularities at the boundary. Allard, which I believe was multiplicity 1 with a convex barrier assumption. More recently, Hirsch, Marini, Delelis, Narduli, Steinbruchel. But the latter two were in 2D only, as far as I'm aware. And then there's also Delelis, De Philippis, Hirsch, Masachesi. Probably some others that, again, I've forgotten, my apologies. But yes, there's boundary regularity is a whole other question, but yeah, here we focus on interior regularity. So yeah, we say that a point is regular if it's an interior point and there exists a neighborhood of this point such that, so locally around this point, your surface is really a single smooth guy with some integer multiplicity. So for some q integers, some C1. Okay, and m-dimensional. And consequently, we say that a point is a singular point, and we say T. Again, interior point is a singular point, right? X is in T. If it's not a regular point, so X is not in T. So the singular points of our m-dimensional integral current are those where you can't find a neighborhood of this point, such that in this neighborhood your surface is really a single smooth guy with some integer multiplicity. Okay, so what are some examples of area minimizers with singularities? Well, of course, probably the most well-known one in codimension 1 is Simon's cone. So codimension 1, Simon's cone. This is the cone over the product of spheres S3 cross S3, which you can write as the points in R8, such that you take the product of the first 4 components squared is equal to the product of the last 4 squared. Right, but this is, I can also write this as the cone over S3 cross S3. So this is Bombieri, De Giorgi, and Giusti showed in, I think, in 69, that this is area minimizing. And it has an isolated singularity at the origin. I mean, yeah, maybe it's not so easy to picture this, and unfortunately if any pictures you do see anywhere, they're not particularly enlightening, because usually they exploit the symmetries of this cone and you really just see like 2 straight lines or something like this. But yeah, this is really, it's a 7-dimensional area minimizing cone in R8, and it has an isolated singularity at the origin. Okay. And then what about higher codimension? So in codimension 2, for example, you can consider the following. So you can consider the 2-dimensional current induced by the points in C2, which you can identify with R4, such that W squared is Z cubed. So if you identify C2 with R4, then this is a 2-dimensional area minimizing surface coming from this holomorphic subvariety with codimension 2. And this has so it has this kind of branching behavior around the origin. You could think of this as like the complex graph W is Z to the 3/2 over the complex plane W equals 0. And this has, again, an isolated singularity at the origin. And you see this kind of 2-sheeted behavior over this plane. So it's forming sort of a 2 cover of this plane, W equals 0. And yes, this has an isolated singularity there at the origin. Again, I'm not going to attempt to draw this, but hopefully you can have some kind of idea of what's happening here. It's really this kind of branching behavior. And locally around the origin, you can't ever decouple these 2 sheets. Okay, so now you can ask sort of, what about in general? Like, how sharp are these examples? And also actually something I should mention is this codimension 2 example. It's a particular case of a much larger class of examples of, so this is area minimizing, and it's area minimizing because it's calibrated. So just write what calibration is. So we say that an m-dimensional current is calibrated if you can find an M form that is closed, has comass at most 1, and such that when you test your current against this M form, this realizes the mass of the current. And for any holomorphic subvariety, this is the current induced by this guy is calibrated by the Kähler form. And it turns out that, calibrated currents are area minimizing. And this is really a one-line proof. Why is this? So I can write this. So why is this the case? Well, you take, you have the mass of your current, which is this current tested against this particular M form, this calibration. But now, because this guy is closed, this is the same as T, this is the same as any competitor applied to this M form. But this is an arbitrary guy in the same homology class as T. So, and this, because your M form has comass, because your M form has comass at most 1, this is less than or equal to the mass. So yeah, it's really very, very trivial proof. So this allows us to come up with examples of area minimizers that come from calibrated things. Okay, right, but now, coming back to what I was saying for this, these two examples I came up with, how sharp are they? So what about in general? How many singularities can an area minimizer have in general? And it turns out that yes, actually, both of these examples are sharp, and the picture is very different depending on whether you're in codimension 1 or higher codimension. So let me write what is known. So known results. So in codimension 1, you have that if M is at most 6, then the singular set is empty. And this was due to the work of many people, including De Giorgi, Fleming, Armgren, Simons, many others that I'm sure I've forgotten. So again, in general, if I forget any names, I'm very sorry. Then if M is 7, the singular set is discrete. This was due to Simons, Federer, Cambieri, De Giorgi, Giusti. Okay, and in higher dimensions, so if M is at least 8, you have the dimension estimate on the singular set. So it's at most M minus 7. And also you have rectifiability. So singular set is M minus 7 rectifiable. So this was due to Federer, and the M minus 7 rectifiability, I believe, was due to Simon in 95. Okay, so that's the picture in codimension 1. So this Simon's cone is, it's sharp. I mean, it's the example that you start seeing non-trivial singularities at dimension 7, and indeed, there you just have this one singularity. So yeah, it's consistent with this. Okay, so before I state what happens in higher codimension, a reason why, so in codimension 1, the picture is somehow much clearer and things are better understood. And this is because in codimension 1, you have this very convenient characterization of area minimizing integral currents, which tells you that locally they are a superposition of boundaries of Kachopoly sets, of top-dimensional Kachopoly sets, or sets of finite perimeter. So I guess remark. In codimension 1, area minimizing integral currents are locally superposition with multiplicities, of course, of m-dimensional, of boundaries of m+1 dimensional Kachopoly sets. Okay. But this is no longer the case in higher codimension. But I'll come to this in more detail soon. I'll explain why we see such different behaviors in codimension 1 and high codimension. So what about codimension at least 2? So here, if M is 1, singular set is empty. If M is 2, the singular set consists of, so it's discrete, but it consists of purely isolated singularities. This was due to Chung, I think in 1988, student of Armgren, but Chung's work relied very heavily on the result of Armgren, which is the general case, so the dimension estimate, which I'll come to in a second, and it relied on the existence of an object known as the branch center manifold, which it wasn't, Chung didn't prove rigorously that this thing exists, and it turns out that it's actually non-trivial to show the existence of such a thing. And more recently, Delelis, Spadaro, and Spolaor, in a series of papers, showed the existence of this and made Chung's proof more transparent and simplified some aspects of it. And also they actually proved this kind of result with isolated singularities for a more general class of currents. So not just area minimizing two-dimensional currents, but also currents coming from the links of three-dimensional area minimizing cones and semi-calibrated currents, which are almost minimizing in a sense. But okay, and then in general, so if M is 3, we have the dimension estimate due to Armgren, which says the Hausdorff dimension is at most -2. This is, as many now call it, Armgren's big regularity paper in the 60s. But more recently, this was Armgren's proof was simplified and made more transparent, more readable by Delelis and Spadaro, who also relaxed the a priori assumption on the ambient manifold. So if I didn't say this already, all of this is posed in an ambient Riemannian manifold. For simplicity, you can think that it's just in Euclidean space, but yeah, you just need some sufficient regularity assumptions on this manifold to like, so yeah, Delelis and Spadaro showed that it's enough to ask for C3 alpha regularity of this ambient guy, whereas Almgren initially asked for C5. Okay, but there's no, first of all, notice that there's no rectifiability, there's no structure result here for in general dimensions. This is still unknown. And yeah, for a long time, and I think still the work of Almgren and Delelis and Spadaro is not so well understood by many. It's very heavy and sort of involved argument. And my plan is to go through the key steps of this and to discuss a recent result of mine where I improve this to a upper Minkowski dimension estimate. So we in fact have an upper Minkowski dimension estimate, as in also n-2 on okay, this is a little bit delicate, but it's on the set of points of densities between some given arbitrary integer and q plus epsilon for all q. And you know, you have to, this is local, so it's on like the, say some like compact set. So this is compact. But yeah, you have this local upper Minkowski bound as well. But this doesn't tell you anything sort of quantitative about the m-2 dimensional Hausdorff measure or Minkowski content. Unfortunately, it just gives you this improved bound. We still don't know how to, it's not yet known how to pack these singularities well at the m-2 dimensional level. Okay, so I think now is maybe a good time to take a break, but after the break, I'll discuss as promised, the key difference between codimension 1 and higher codimension, and then I'll discuss the key aspects of the proof of Almgren and Delelis and Spadaro, and I'll explain which bits we have to change or strengthen in order to get this n-2 dimension upper Minkowski dimension estimate.